Okay, so transmission lines and antennas. So this is how you connect your transmitter and your receiver to your antennas. There's some interesting antennas there. The one on the right, anyone have a guess what it is? It's the woodpecker. Spot on. It's the Juga array, which is a stone's throw from Chernobyl. So it was all shut down when Chernobyl went bad. But it's in amateur circles on 40 metres and a couple of other frequencies. We used to be plagued by what we called the woodpecker. It's like that. And it was an over-the-horizon radar that the Russians used. So, very famous array.
After it was off?
No, that was pre-Chernobyl.
Oh, right.
Pre-Chernobyl. So, and yeah, it was just referred to as the woodpecker. And now we just deal with Jawn, so our own. Okay, so this is connecting your transmitter to your antenna. Sometimes called a feeder because it feeds the antenna. The concept you need to know is the size of your antenna depends on the frequency to which you're transmitting, and it's an inverse relationship. So it's at higher frequencies there's smaller antennas. At lower frequencies, longer, larger antennas. The other concept is impedance. We call resistance in an AC world, so an alternating current world, we call impedance. So you'll hear what is the impedance of your antenna, or your characteristic impedance of your antenna, or characteristic impedance of the output of your transmitter. And that'll become clear in a sec. Now, as part of the practical, we'll get you to identify balanced and unbalanced line. We've got balanced line, or ladder line. This used to be really popular as a television antenna. You could make a really cheap, really quick television antenna with 300 ohm balanced line, ladder line. And then it's what we call balanced line. So, in the sense of it has two conductors. If there is the way to think about it is, if there is some sort of interference or some sort of external signal that is cutting across this particular line, it cuts across equally both lines. And so, in the configuration of the antenna you've got, that signal gets nulled out because it's actually on both sides of the balanced line. So that's why we call it balanced line. Versus unbalanced line, which is what you would normally see, which is coax. Now, all sorts of different sorts of coax. And in fact, even all the way up to... no, it's not there. Really big coax, which is somewhere there. No, don't worry. Really big coax. This is what we call unbalanced line, because there is a centre conductor which has a big shield around it. And it shields that centre conductor. Unbalanced line. Usually 50 ohms or 75 ohms. 75 ohms in the television industry. It's still 75 ohms in the television industry, 50 ohms everywhere else. But we'll get you to identify that as part of your practical. We also get you to test transmission lines with a continuity tester on a multimeter, and we'll show you what to do. And we test. The key thing about testing coax lines or any lines is you test that there is continuity between one end and the other on the centre conductor and the outside conductor, because it's a bit of coax, but you also test centre to outside conductor, because if you happen to have created the cable and you've created a short, which is really easy to do, you need to know that there isn't a short there. So continuity on the inside conductor, outside conductor, and not continuity between the inside and outside conductor. We'll go through all of that with you. You need to be able to identify different types of RF connectors. So we've got a whole, there are 3 different types. The outside one here, so that's the plug and the socket, is called an N-type connector. And in fact, what I'll do, so N-type plug socket, UHF plug socket, and BNC or bayonet cap plug socket. So we'll have a picture much like this and point at them and get you to say, is that what sort of connector is that? So that's a bit of the practical. Now we have this concept of, we've got balanced line that we want to connect to, unbalanced line that we want to connect to a balanced antenna. Now a balanced antenna, in this case, this is what we call a half wavelength, and there's a little half and a little lambda symbol. Now the lambda symbol is the symbol for wavelength. So that's telling me it's a half wavelength balanced antenna or dipole, because there's 2 poles, one on each side, exactly the same. So this is what we call a half wavelength dipole. Now that's a balanced antenna because they're both exactly the same, and we want to connect it to an unbalanced line. We need to do a little transformation called a balun, or a balance to unbalanced transformation. And that's a balun. And a balun can also change the impedance or the characteristic impedance from one thing to another, because this is 50 ohm line that we want to get to, and our transmitter's expecting 50 ohms, and our dipole is not 50 ohms, 72 ohms. So we usually do a little bit of a transformation, impedance transformation on the way through. Okay, an antenna couples our RF energy to the space around the antenna. This is the magic bit. Always refer to this as the magic bit. So it radiates an electromagnetic wave. Now, what that's telling you is there are 2 components to that wave that it transmits. There's an electrical and there's a magnetic component to it. I'll go into that in a bit more detail in a sec. The antenna should be resonant. Now, here's that word again. Resonance. Needs to be resonant at the frequency you're transmitting at. And that's so hopefully all or most of the energy that you're generating in your transmitter is actually transmitted out the antenna. If it is not resonant at that frequency, then you might as well stop transmitting, because most of the energy that you're generating in your transmitter is actually going somewhere else. It's being absorbed by the feed line, the transmitter, etc. And I'll go into that in a sec. There is this concept that if it is resonant, an antenna is resonant and it transmits really well, it will receive reasonably well as well on that particular frequency. Antennas are affected by everything. So whatever the environment it's in, it is affected by the ground that it's above. It is affected by the buildings that is around it. It's the trees, the moisture in the air, the moisture in the ground. You can set up an antenna one day and tune that antenna, and it's fantastic, and go back the next day and it's not. Or it's different. So it is affected by everything around. I said that there were 2 components to an electromagnetic wave. One is the electrical lines of force and the magnetic lines of force. They are at right angles to each other. And we also, this introduces this concept of there being polarization. Now we talk about an antenna being vertically or horizontally polarized. So if an antenna is, what do you think the polarization of this particular antenna is?
Vertical.
Great. Fantastic. That's simple. And it's the electrical lines of force that determines the polarisation. So, and you need to have the polarisation of your antenna matched, because if one is horizontal and one is vertical, there is a whole lot of loss introduced. There is quite a bit of loss introduced. So, for best results, transmitters and receivers polarisation should be matched.
Why don't people use circular polarisation?
Different polarisation type altogether. For satellites, we use circular polarisation, well and truly.
Wouldn't that give you better point-to-point contact if you don't know if you're going over water or not?
Yeah, spot on. And as it travels through, as signals travel through the atmosphere, they change their polarisation. As they bounce off of things, they change their polarisation. And so, that's why a lot of antennas you'll see at 45 degrees. Because it's halfway between vertical and horizontal. So you don't actually get as much loss, but it's more likely going to pick up enough signal for you to be able to receive the signal. So all sorts of things. Foundations don't need to know about circular, but it is for satellite communications. You are actually transmitting in either a left or a right-hand circular polarisation. And it deals much better with the changes through the atmosphere. So, and the fact that satellites are tumbling and all sorts of things. So, now, as part of your practical, you need to identify, so we're going to show you some pictures of antennas without labels on them. And you need to be able to identify what type of antenna they are. This is called a half-wave dipole, and that is because you'll notice that there are two poles, one on either side, exactly the same size, and they are cut to particular lengths, half wavelengths. It is what we call a broadside or a bidirectional antenna, because if we plot the radiation pattern that comes off of it, it looks like a donut. So off the ends there is signal off the ends, but there is much less signal than front on. And it's horizontally polarised. It's horizontal. Folded dipole. So if we take that dipole and we turn it around and into a loop, we have a folded dipole. Now the thing about a folded dipole is it can be, dependent on its orientation, it can be a broadside antenna. And you'll notice, actually, if you take a notice of some of the antenna towers around town and up on hills and all of that sort of stuff, you'll see these quite often. These are very popular commercial antennas, and you'll see these in all sorts of orientations. You'll see one that's horizontal, one that's vertical, one that's at 45 degrees, and it's a very good way of cutting down or reducing the interference from other services on that site. So you'll see these in all sorts of orientations. If they are in that sort of orientation on the picture, it's an omnidirectional orientation. It's the donut flat on its side, on its face. Whereas if you turn it so that it's horizontal, it's actually a broadside antenna that is in two different in two different directions. And then if you turn it the other way, you've got slightly different polarisation. So they're very versatile and very robust antennas. They can take a lot of ice when they're on a mountain. They're very very popular commercial antennas. And I talked about television antennas using 300 ohm line. If you get a coat hanger and you bend it round and you connect it to a bit of 300 ohm line, that's actually pretty close to where the television signals are, and it's a great little folded dipole antenna. Really quick, really dirty, works really well. People don't do that anymore, but they used to. That's what we use 300 ohm line for. Now, quarter wave. This is probably one of the simplest antennas you can actually make, because you can make it on an antenna socket. It has a quarter wavelength vertical, and then it has what we call quarter wavelength ground planes that come out in the horizontal. And those radials are just a little bit longer than the quarter wavelength radiator in the middle. It's vertically polarized, it's a donut, and it's what we call an omnidirectional antenna. It transmits in all directions, although not very good for satellite work because there's not much that goes up. If you then, this is the magic trickery of antennas, if you droop those ground planes down at 45 degrees, the characteristic impedance of that connector is 50 ohms. You don't need to do any more matching. So that's a really popular antenna. You basically make all of that with bits of wire on a antenna socket and you've got yourself a quarter wave ground plane. A Yagi. Okay, Yagi is a unidirectional antenna. So you have what's called a reflector, which is usually the longest. There is a director. There's a driven element in the middle. That's where your coax is connected to, and then you've got any number of directors. In this case, there's only one, but the directors there can be. If I go to the next one, here's one that has 19, I think, directors on it. As you put more and more directors on it, it makes it even more narrow in beam width. And so this is one that's pointed at Mount Wellington. We have a little net that goes on a Sunday morning where everyone points their Yagi antennas at Mount Wellington, and we use Mount Wellington as a passive reflector. So you can get all the way down to Kingston and Huon, all the way up into the Derwent Valley, all the way over down to the Tasman Peninsula, etc., all using Mount Wellington as a passive reflector. So that's a Yagi. It is unidirectional. Now, unidirectional enables us to introduce a concept called gain. So if you're directing all of the energy that you're putting into the antenna in one direction, there is this concept of there being that antenna having gain. So it's got a lot more radiating potential, if you like, in one direction. So, and this is where foundation licensees need to know the concept of decibels, but you don't need to know the mathematics behind it. We measure gain in this logarithmic scale called decibels. Now the fact it's logarithmic, the one thing you need to know and remember is if I say it's got 3 dB of gain, it's 2 times the gain that it's got. 3 dB, 2 times the gain. And there's the other, and because it's logarithmic, we get to 10 and it's 10 times. So if I say it's got, that particular antenna's got 3 dB of gain and I'm putting 10 watts into it, what am I getting out of the front of it? 20. Correct.
It doesn't seem to be, like there don't seem to be license conditions that apply to your ERP.
Oh.
Is that just because it's
Not
too
for
hard to
foundations.
police? Or is it just like a within reason type of thing? Because couldn't you basically like make something a laser and then you would be interfering with all sorts of stuff?
You can.
You'd be outputting so much power.
But you're limited to 10 watts input.
Yes.
Now, there aren't that many antennas around that give you, apart from probably dishes, maybe, that give you a scary amount of gain. So 10 watts, don't worry about it.
Right.
You're not going to get to a point where it's scary. At 400 watts, you probably would get to...
Front gate's all yours.
Cheers, thank you. You probably would get, at 400 watts with a dish, you probably would get to some scary EIRPs. So yeah. But for a foundation licensee, with only 10 watts to use, this could be advantageous. It could be quite advantageous.
Right.
Especially on 2 and 70. On on HF, yeah, okay, there is some advantage, but on 2 and 70 with a Yagi, you can do pretty well. But there's this, so it introduces this concept of an antenna having gain, and when antennas, there are lots of snake oil salesmen out there in the antenna business that go, oh, my antenna's got much more gain than your antenna. And you go, really? So you have to be a little bit careful there. But it's this concept of that power that you're putting into the antenna can be directed in a particular way. And that's where there is this concept of gain introduced. If it's just a dipole, yeah, you might get a bit of gain in the donut direction, but it's not really that much. So anyway, the effective radiated power (ERP) of the transmitting system is increased, and that's within your license. You can do that. You can well and truly do that. The other antenna that we will get you to identify is an end fed. Now, the way you identify this is where is it being fed? A dipole gets fed in the middle, an end fed gets fed at the end of the wire. Now, it's omnidirectional, it radiates in all directions. It usually requires an antenna tuning unit because it has some funny characteristics. And it's usually half wavelength or longer in quarter wavelength multiples. And it can operate across multiple bands because your antenna tuning unit enables you to match the antenna. It doesn't tune your antenna, it matches your antenna. I'll go into that in a sec. We introduced the concept of there being impedance, which is AC resistance. Most of the transmitting equipment that you will be exposed to is 50 ohms. Televisions still use 75 ohms, so if you plug in a television antenna, it is actually 75 ohms. And the output of the transmitter should be matched to the characteristic and impedance of the... Hello, Reg. Now, this is the person that most of you spoke to. This is Mr. Reg Emmett. So welcome, Reg. So mismatch of transmitter outputs should be avoided for a whole range of reasons. The main one is causing interference, but also if you've only got 10 watts to play with. So if you're mismatched your transmitter to your antenna, most of that power is disappearing. It's not being transmitted. So you're really pushing it uphill. So matching. Now, that mismatch causes what we call standing waves on your feed line. So most of that power sits there and goes backwards and forwards on the feed line, not being transmitted out of the antenna. So that's what you want to avoid. You measure this with a standing wave ratio meter. So what it does is it measures the power going out versus the power being reflected back, and it's the ratio of those two. Most transmitters and transceivers these days have built-in SWR meters, or there can be an external SWR meter. In the practical, we'll actually get you to put these together, and we'll go through what that is in a sec. And each time you change frequencies, it's probably a good idea to actually check your SWR, because if your SWR suddenly goes up, you're not transmitting all that power. So you want to make sure that you are. And we'll actually show you in the practical the ability, what mismatch looks like in SWR terms. We got a little test antenna sitting there that we'll actually be using during the contacts you'll make too. Now, as a foundation licensee, you need to know that an SWR of more than 2 to 1, and we'll show you how you read that off the meter. More than 2 to 1 is likely to indicate a fault in the system somewhere. Probably worth a look at your antenna. A good SWR is 1.5 to 1 or less. 1 to 1 is a perfect match. Now, can I just say, we very, very rarely have a perfect match because of characteristics of what's around the antenna and feed lines and all sorts of stuff. But if you can get 1 to 1 match, you're doing really well. Anything below 1.5 to 1 is considered to be a pretty good match, and you operate. You well and truly operate. There's a couple of different types of